Okay.
Can you say again, Professor?
Oh, I can't hear you anymore.
One more time.
Yeah, I can hear you now. Can you hear me?
Yes, yes.
Perfect. All right, so why don't we get started? Welcome and good morning to everybody in Marcus and everybody joining us on the live stream. I hope you guys are having a good day. So hopefully you received my emails. There were obviously intermittent issues with Moodle. And so both the 3.4 mini quiz and the chapter 3 quiz got extended through the end of today. So if you were not able to access Moodle to complete those, you hopefully will be able to access it today, and hopefully these issues will resolve. I'm not entirely sure what's going on. There were definitely periods where I couldn't get into Moodle and I was having trouble accessing the gradebook and other features, but hopefully it'll be all resolved today. So we are moving into chapter 4, and just to sort of give you the big picture of what we're doing in chapter 4, we think about what we did in chapter 3, which was our derivative techniques. So we learned how to take the derivatives of all sorts of types of functions. And chapter 4 says, okay, well, what kind of information can we get now that we're really comfortable taking derivatives? So we're going to be taking what we learned in chapter 3 and applying it to see what we can learn. So I'm going to go ahead and switch over to the DocCam. Okay. And so one thing I want to talk about is this particular section, local max and min, is pretty long. So we're actually going to cover it today and Thursday. So the mini quiz for this section is on Sunday. So there's no mini quiz on Wednesday of this week. So what we're looking for in this section is how do we identify what we're going to call local maximums and local minimums. And we have to be a little bit careful about our definition, because next week we're going to learn about what we call global maximums and global minimums. And we want to make sure we understand the distinction. So what we're going to do is we're going to talk about what local maximums and minimums are, but then we have to take a step back and build up the process of how we find them and identify them. So a local maximum. So the definition of a local maximum, we say a function is said to have a local maximum, and we will often just say local max, but local maximum at p. So this is an x value. So when x equals some number p. If f of p, so if the y value is greater or equal to values of f of x near p. So it's kind of an awkward definition, and we're going to do the definition for local minimum, and then we're going to look at a picture to really understand what this means, okay? So as you probably guessed, the local minimum is going to be very similar in definition. A function is said to have a local minimum, which we'll often call a local min, at P if f of P is less than or equal to values of f of x near P. Okay, so what does this mean, like near P? So I want you to look at this picture so we can talk about what a local max and a min are. So when we talk about near, what we're doing is we're looking for areas where there's a very distinct lowest value or highest value. So for example, right here, this is a local minimum. Okay, it's a local minimum because it's the lowest y value in an area of f of x. Okay, this right here is also a local minimum because in this area, it's also the lowest value for a sort of chunk of f of x. And so what I want to point out is that we have multiple local minimums. And this is going to happen whenever we're sort of at the bottom of one of these cups, like a U shape. And we're going to have local maximums whenever we're sort of at the top of a hill. Okay. So what are some things that we notice about this? Okay, so first, functions can have more than one local max or min. So there can be multiple. We see in this picture that there's 2 local minimums, okay? And that local maxes and mins do not have to be the absolute highest or lowest point. Okay, and I bring that up because when we hear the word maximum or minimum, we often think the biggest and the smallest. And that's going to be true when we talk about global or absolute maximums and minimums, but those are different than local. So local means in a small area. So here you can see that this local min down here is also an absolute minimum. It's the lowest point on the graph. But this local max is not the absolute maximum. There are definitely points that are higher than this on the picture, and that's okay. So local means that, you know, we're just looking at these small areas where we're at the bottom of this sort of cup or the top of this sort of hill. Okay, so that's what we're trying to find. So our goal through class today is going to be thinking about how do we figure out where these things are? How do we talk about them, right? And how do we get there? So we're going to build up from the ground how we find these points first, right? So the idea is we're going to determine where these things are, and then we're going to learn how to determine if they're local maxes or local mins, right? Because these are sort of two steps in the process. So we start with what's called a critical point, okay? And so a critical point P, and so again, this is an X value, which will make more sense in a few minutes, for a function f of x is a point in the domain. Remember we talked about domain and range. So the domain of f of x, so things that we can plug in, where f prime of p equals 0, or where f prime of p is undefined. Okay, so a critical point is going to be where your first derivative equals 0, or when your first derivative is undefined. Let's talk about undefined for a second. This typically only happens if you have a quotient, right? That's the sort of most common way. And so that comes up when we do things like the quotient rule. We have to check the denominator. Is there a place where the denominator equals 0? But most of the time, what we're looking for is where the first derivative equals 0. So what that does is it takes our derivative techniques and we say, okay, what's the first derivative? And then we pair that with algebra and say, when does this derivative equal 0? Okay, the critical value is a value of f of x when you are at the point x equals p. So f of p. So this is the y value when you plug in the value you found for the critical point. So what does that mean? That means when we determine critical points, which we are doing the majority of the time, we are finding the x value where we have this critical point. Now, why do we want this critical point? So what I want you to notice back in our picture is that this local max, if we were to draw on the tangent line, that's a horizontal tangent line. And for our local mins, if we were to draw on the tangent line, these are also tangent lines. So what does that mean? That means at these points where we have local maxes and mins, the derivative equals 0. Okay, so critical points are a way for us to find all the places where we have horizontal tangent lines. So this is going to help us identify where we would have local maxes and mins. We won't know yet if they are local maxes or local mins until we do other work. But for today, we want to find all the places where these horizontal tangent lines exist. And so those places, those are called critical points. Okay, so let's see what this looks like sort of in practice here. So today there's going to be quite a bit of algebra. So hopefully it's not too tricky. We'll see how it goes. So we're going to start with this function here. Suppose f of x equals 3x squared plus 6x plus 1. We want to find all the critical points of this function. So what I would like you to do is I'm going to give you 2 minutes since it's our first one. I want you to find the first derivative of this function and determine where the first derivative equals 0. Okay. Actually, you know what? I think we'll do 2 of these at once. These are going to be very similar. So let's do example 1 and example 2. So the first one is 3x squared plus 6x plus 1. We're going to find the first derivative using the power rule, set that equal to 0 and solve for x. And for example 2, we're going to do the same thing. We're going to find the first derivative of the function, set it equal to 0 and solve for x. The difference between 1 and 2 is that when you do example 1, you can solve just with things like addition and subtraction, whereas for example 2, you are going to need to try to factor it or use the quadratic equation. Okay, so I'm going to give you, let's say 3 minutes, see if you can figure these out. At least you should try to make sure you get the first derivative correct, and then if the algebra sort of trips you up, that's okay. We'll walk through it together in about 3 minutes. So try those 2 out. Okay, take about 30 more seconds. Okay, so let's check these out. So whenever we see that we're looking for critical points, we are thinking, when does the first derivative equal 0, or when is the first derivative undefined? So our first step is always going to be to determine what the first derivative is using our derivative techniques from chapter 3. So here we're using a power rule. So when we take the derivative of 3x squared, the 2 comes down to multiply the 3, and we get 6x plus the derivative of 6x is 6, and the derivative of 1 is 0. Once we have our first derivative, we want to know what x value makes that equal to 0. So in order to solve for this, we're going to subtract this 6 to the other side. So we have 6x equals -6. We divide both sides by 6. And we get x equals -1. So we have a critical point at x equals -1. So what that tells me is that for this function, I am going to have a horizontal tangent line at x equals -1. So that means it's a good candidate for a place where I might have a local max or a local min. Again, we're going to learn later, either at the end of class today or on Thursday, how we determine if that's a local max or min. But for right now, we're trying to figure out where these things happen. Okay, let's look at example 2. So again, we're going to start off by finding the first derivative. So here we had 2x cubed. So when we take the derivative, the 3 comes down to multiply the 2. You get 6x squared minus, here we're going to get 6x minus 36. And then the derivative of 14 is 0 because 14 is a constant. So we want to know, when does that equal 0? Now, there are a lot of ways algebraically that this can be solved. You can use the quadratic equation. There's different ways to factor it. So I'm going to factor it the way that I prefer. But if you did it slightly different, as long as you're coming to the same solution, then that's totally fine, because there's a lot of different ways that you can algebraically solve this from this point. So for me, I like to factor out the term in front of x squared first. So I'm going to pull the 6 out. So I have x squared minus x minus 6 equals 0. And then I'm going to factor what's left in the parentheses here. And so I'm looking for two numbers that multiply to give me -6, but add up to give me -1. So that's going to be x minus 3 and x plus 2. Okay, so -3 times +2, those multiply to give me -6, but add up to give me the cross term of -1. Okay, so now I have 3 distinct factors multiplied together equals 0. If you have things multiplied together equals 0, one of them has to be 0. We know that 6 is not 0 because it's 6. So I set each factor equal to 0 to solve. So x minus 3 equals 0 would have a solution of x equals 3. And if I set x plus 2 equal to 0, that's going to give me the solution of x equals -2. So these are my two critical points. Okay, so these are the two places on this function where I'm going to have horizontal tangent lines. Okay, so we're going to be doing more of this, just taking this idea that we're interested in where the first derivative equals 0. So let's go ahead and try. Okay, yeah, let's do Example 3, so we have x squared over x minus 2. I'm just going to write that a little bit bigger. Okay, and so we're interested to find all the critical points of this function. Okay, so notice that we have a quotient here. So we're going to have to apply the quotient rule. And as a reminder, when we're looking for critical points, we're looking for where the first derivative is 0 or where the first derivative is undefined. So because we're going to have a denominator here, we will have an instance where something might be undefined. So just be careful about that. And see what you can figure out. I'm going to give you about 2 minutes to try this one out. See what you can do with the quotient rule. You will have to simplify it a little bit and think about when quotients equal 0, but hopefully you remember that from algebra. If not, just get as far as you can and we'll go through it together in about 2 minutes. Okay, take about 30 more seconds. All right. So here, again, I started with a quotient, so I'm going to be applying the quotient rule. And the quotient rule says that my top function has to be my f, and then the bottom function is going to be my g. Then I want to take each of their respective derivatives, and when I put it back together in the quotient rule, I am going to get f prime times g, so I have 2x times x minus 2. You're going to want to use parentheses whenever you have more than one term, minus g prime times f, so 1 times x squared, all divided by g squared. Okay, now, if we were just doing the product rule, just to find the derivative, we wouldn't need to do any simplification. But since we want to determine where this function might be 0 or it might not be defined, we do have to do some algebraic simplification before we can set that up. So in the numerator, if you distribute this 2x, you're going to get 2x squared minus 4x minus x squared. I'm going to leave the bottom as is. And now notice that on the top, I have a 2x squared and a minus x squared. So I can simplify that. And I have something that looks like this. So if I want to know when a quotient equals 0, that will only happen if the numerator equals 0. So I can actually separate out the numerator term to set equal to 0 for the first part of what I need to do. So I'm going to take that numerator, x squared minus 4x, set that equal to 0. Okay, so I notice that I can factor out an x. I'm left with x times x minus 4 equals 0. So again, now I have two factors multiplied together equals 0. That means one of them has to be 0. If I set x equal to 0, then I get x equals 0. So I will put that over here. I'll start making a list. And then if I set x minus 4 equal to 0, I get x equals 4. So I have these two critical points. From setting the numerator equal to 0. We also know that we have critical points when the function is undefined. So here, what I need to do is I need to check if there's a way that the denominator could ever equal 0. So I set that up. So x minus 2 squared equals 0. So if the denominator equals 0, then the function is undefined. And I see that that happens when x equals 2. So if x equals 2, this becomes 0. 0 squared is 0. So that means that x equals 2 is also a critical point. So this function has three critical points, 0, 4, and 2. 0 and 4 came from when the function equals 0 because the numerator equals 0, and x equals 2 came about because that's where this derivative is undefined. Okay, so that's how we find the critical points of that type of function. The next one that we're going to do is really about the algebra. When you sort of get into the nitty gritty of it, it is about derivatives as well, but this one is a little challenging algebraically. So I want you to try your best to do this, and I'll sort of give you a few hints, but this one definitely is on the harder side of things. So here we're talking about the function x cubed times 1 minus x to the 4th. And I'll write that just a little bit bigger. Okay, and we're trying to find the critical points of this function. So the first thing I'll say is that we're going to do a product rule to start. Because notice we have x cubed times 1 minus x to the 4th. When you do this product rule, I want you to notice that the 1 minus x to the 4th term, you're going to have to do a chain rule. Once you have your first derivative, then you need to think about how you would factor it to determine the critical points of this function. So the factoring is not super easy, but it is definitely attainable, and we will go through it obviously step by step once you've tried it. But give it a try. See if you can get at least the first derivative, even if you can't get it factored. We'll go through the factoring together. If you're comfortable with factoring, then you should be able to figure out what to factor out. But give it a try. I'll tell you that there's three critical points in the end that we're going to find for this function, if that's helpful. But try it out. Again, we're going to start with a product rule. You're going to find the first derivative, right? These are the two things being multiplied together. I'm going to give you about 3 minutes because this one is kind of long. Try it out, right? And we'll see what happens, and then we'll go through it together. Okay, take about 30 more seconds. All right. So here we're doing a product rule, and the two things we're multiplying together are the x cubed and the 1 minus x to the fourth. So we need to find each of their respective derivatives so that we can put everything back together in the product rule. So the derivative of x cubed we can do with the power rule, and we get 3x squared. However, when we take the derivative of 1 minus x to the fourth, we have to do a chain rule here. So I'm going to use the shortcut, but it's totally fine if you use a z substitution. So here I'm going to do the outside part first. So here the 4 comes down, everything inside stays the same, and we subtract 1 from the power. So we get 4 times 1 minus x all cubed. And then we have to multiply that by the derivative of the inside. So the derivative of the inside is a little tricky because we have minus x, which means that the derivative is minus 1. Okay, so we can take that negative 1 and it can multiply the 4, and we can write this as minus 4 times 1 minus x cubed. Okay, so now when we put this together in the product rule, we're going to do f prime times g. So we have 3x squared times 1 minus x to the fourth plus g prime times f. But since there's a minus here, I'm going to do minus 4 1 minus x cubed times x cubed. So our derivative looks like this, okay? And we want to know, when does our derivative equal 0? So this is the first part that's really sort of, you have to be really careful. There's a lot of times you can lose a negative or something like that. So if you were able to get the first derivative like this, that's great. Okay, now we need to think about how we factor this. And for some people, it's been a long time since you took algebra. And so we're just going to review how we think about factoring so we know how to do it in the future. So when you have something like this, we really have two terms that we are evaluating. Okay, the first term is this whole piece right here, and the second term is this whole piece right here. Okay, because they're all multiplied together within the term. What we're looking for are commonalities between the terms, right? So what do they have in common? And so the way we think about this is first we start with the constants. We see if there's a constant that can be factored out, that could be factored out of both terms. So here the constant is 3, and here the constant is 4. So there's not a constant that we can pull out that would both go into 3 and 4. So we're not going to take out a factor that is a constant. The next thing we want to do is we want to look at the types of factors. So the next thing we would look at is this x squared. And we notice that we have an x squared and an x cubed. So both of these are an algebraic factor that have an x in the base. So what we do when that happens is we pull out the factor with the lowest power, right? So we have an x squared and an x cubed. That means we're going to pull out an x squared, okay? The other factor that's in both terms is this 1 minus x factor, okay? So we have a 1 minus x to the fourth and a 1 minus x to the third. So again, we're going to pull out the one with the lower power. So we're going to pull out a 1 minus x to the third, okay? So once we've pulled out the things that are in common, we need to ask what is left. So go to the first term. We have a 3. We didn't pull out a constant, so that first term still has the 3. The next term is an x squared. We pulled out the entire x squared, which means that there's no x terms left. And then the last term was 1 minus x to the fourth. Well, we pulled out 3 of the 4 of them, which means we're left with a 1 minus x to the 1 power, right? Because we pulled out 3 of them, there were 4 of them, so there's 1 left. Now from the second term, we see that there's a 4. We didn't pull out any constants, so the 4 is still there. The next thing we have is the x squared. This was an x cubed, so we pulled out 2 of them, but in this factor there were 3 of them, so there's still an x to the 1. And then the 1 minus x cubed, this is 1 minus x cubed, so we pulled out all of them. Okay, so that is what's left after we factored out these 2 terms. Now, the factored terms, we'll call them 1 and 2. Once they're pulled out, we leave them as is. But this last factor here, the stuff that's left in the parentheses, we want to see if we can simplify this at all. So what I'm going to do is I'm going to distribute the 3 into this parenthesis, because the parentheses raised to the 1 power. So I have 3 minus 3x minus 4x. And now again, the first 2 factors just stay the same. But what I notice is I have a minus 3x and a minus 4x. So I can combine those to be 3 minus 7x. And again, I'm really interested in when this equals 0, because what I'm factoring is the first derivative. So now what I do is I take each factor. So again, 1, 2, and 3. There's 3 factors. I set each one equal to 0. Excuse me, to find my critical points. So I start with x squared. So if x squared equals 0, if I solve that, that means x equals 0. That's my first critical point. For my second one, I have 1 minus x cubed equals 0. That tells me that x would have to be 1, right? Because I'm considering what's going to make this parenthesis equal to 0. So that's my second critical point. And then I have 3 minus 7x equals 0. So I'm going to bring the 7x over to the other side. So I have 3 equals 7x. So to solve for x, I divide both sides by 7. And I get x equals 3/7 is what makes my third factor equal to 0. So there's 3 critical points. And I get them, again, by factoring out my first derivative. So if it's been a while since you factored, hopefully that all sort of makes sense into what you remember. But there's definitely at least one problem like this on the homework where you do have to factor things like this and then simplify what's left inside to find all the critical points. So again, this one is definitely more on the hard end in terms of the algebra. So they won't all be quite this extensive. Okay, so these that we've looked at so far have all taken the route of being algebraic, right? So we're answering the question, when does the first derivative equal 0? And since we've been given these algebraic functions, we've been using our regular derivative techniques. But again, the big question is, when does the first derivative equal 0? So we don't always have to do this on functions. So let's take a look at this one here. So suppose f prime of x is given in the graph below. So again, this is the derivative graph. Notice that that's what they tell you here. Okay. Use the graph to determine critical points of f of x. So we're looking for critical points of the original function, and we are given information about the derivative on the interval -2 to 8. So just what you see. Okay, so I'd like you to take 1 minute and I'd like you to think about how we can use the graph of the derivative to find the critical points of the original function. Okay, so take a minute to think about what that may look like, where we might find those, and go ahead and take a guess at roughly where those x values are. And then we'll go over it together in just about 1 minute. Okay, so how do we use the graph of the first derivative to figure out the critical points of the original function? So remember, critical points happen when the first derivative equals 0 or when the first derivative is undefined. Okay, oops. So let's talk about undefined first. Undefined on a picture is going to look like something that shoots off to infinity or has a hole. There's nothing like that on this graph. There's nothing here that would say the first derivative is undefined. Okay, so what we're looking for is when the first derivative equals 0. So since this is a picture of the first derivative, we are literally looking for when it has a y value of 0. So those are the places where we cross through the x-axis. So we see that there's 3 critical points here. Okay, this one looks like it happens at roughly x equals 0. This one happens at pi, but you could also say, 3.1 approximately, right? So that's where this crosses. And then over here, you may have noticed that this is 2 pi, or you may have called this something like 6.2. Either one is fine. But the idea is that when we have information about the first derivative, we want to know where the first derivative equals 0. So we are looking for when it equals 0, and what that means graphically is where we cross through the x-axis. Okay, so it's going to become incredibly important to make sure that you know what information you have and what information you want. Because if you're given a graph of the original and you're given a graph of the first derivative, you use those differently to answer the question. Okay. Okay, so let's take a look at a table. Okay, so we're going to say that f and f prime are continuous and they're differentiable. We're given a table of derivative values to determine the most likely place that f of x would have critical points. So I'm not going to say too much about this. I want you to just take a look at this, think about what we know about the definition. I'm going to give you a minute. I want you to think about where you think the most likely places are that we would have a critical point on f of x. So take 1 minute, see what you can figure out, and then we'll go through it together. Okay. So because f of x and f prime of x are continuous, that means that there's not going to be any places where the first derivative is undefined, right? Because if it's undefined at a point, it's not continuous at a point. We learned that back in chapter 2. So that means we are again thinking about where the first derivative, which is what we're using, could equal 0. Right? That's what we're looking for. Here, the data that you're given is f prime of x. So if we look through, we have -14, -8, -4. And then we have this point here where the y value is equal to 0. That happens at x equals 6. So we're going to have a critical point at x equals 6 because the derivative at that point equals 0. Okay? Now, there's another tricky one that's in here that's not quite as obvious. So notice the y values here, 5, 2, -1. In order for your y value to change signs from positive to negative or from negative to positive, it has to go through 0. So that means we're going to have another critical point between x equals 10 and x equals 12 because the derivative changed signs. It also changed signs over here from negative to positive, but fortunately we knew exactly where it happened because it was given to us on the table. Here, somewhere between 10 and 11, or between 10 and 12, again, we have to cross through 0 to get from +2 to -1, right? You have to go through that x-axis. So one of the things I really want to point out here that we've been doing the whole time is when we talk about critical points, we are talking about where they are in terms of their independent value, right? So we're talking about a location. Where is it located? It's located at x equals 6. It's located between x equals 10 and x equals 12, okay? So that's going to be important because, again, later we're going to learn about global maxes and mins, which we use the y value to define. So with local maxes and mins and critical points, we're looking at x values. Okay, so now that we have a good idea of how we find critical points, right, we want to know how do we use those critical points or the information we have about the function to determine if we have a local max or a local min. And there's 3 sort of, oh, just kidding. There's more critical point problems that I didn't realize we had because I didn't flip my page. Okay, let's do these. Take a step back, ignore what I said for a minute. So let's look at here, again, thinking about critical points of a function. We want to be able to do this sort of in general. So what does that mean? That means if we have non-zero constants like a, b, and c, we can still find critical points. They will just have a's, b's, and possibly c's in the solution. So it's about thinking about what the derivative might look like for a generalized function, and also thinking about what the algebra might look like when we solve this. Okay, so for example, 7 and 8, we're really thinking about how we generalize when we're thinking about derivatives in algebra to talk about critical points. Okay, so what I'm going to have you do is I'll give you 3-ish, maybe 4 minutes. The first one shouldn't be too terrible on the algebra if you can figure out what the derivative is going to look like. So you want to find the first derivative, set it equal to 0, and as a reminder, we're solving for x, right? So when we set it equal to 0, we're trying to isolate the x. For example, 8, we have to be a little more careful. We're still trying to see where the first derivative equals 0, but I want you to notice that the x shows up here in the beginning, but also up here in the power, which means that we have to do a product rule in order to get the first derivative. And then there's some factoring involved here, where again, we're trying to solve for x, okay? So I want you to take about 3 minutes, try these 2 out. Again, your solutions is totally fine if they have things like an A or a B or a C in them, or an A or B, because that is sort of the nature of the problem. So try it out, see if you can solve for those, and then we will go through it together. take about 30 more seconds. Okay. So for the first one, we want to start by finding the first derivative of the function. And we can do that using the power rule. We just have to be careful with the constants. So when you have ax squared and you take the derivative, the 2 comes down, but the a is a constant multiple. So our derivative is 2ax of that first term. The second term, the derivative of bx, is just b. And the derivative of minus c is 0 because there was no x term, okay? So for critical points, we want to know when does that equal 0? So again, we are trying to solve for x. That's our goal here. So let's go ahead and move the b over to the other side. We'll subtract the b over, and we'll have 2ax equals minus b. And now to solve for x, we have to divide out 2a. Okay, so it's going to cancel on the left, and we're left with x equals negative b over 2a. So that's helpful because if we have problems in the future where we have values like a is 1, b is 2, c is 3, we know the general form of what the critical point is going to look like. Okay, so that's how we would take the derivative in general for this type of function and how we would solve for when that equals 0. So the critical point here is negative b over 2a. Now, for the second example, ax e to the negative bx, this one is definitely more challenging, right? There's more algebra, there's more sort of setup for the derivative. So we'll just try to be extra careful as we walk through the steps of this. So I mentioned that this is going to be a product rule because there's an x here and an x here, and they're multiplied together. So when we set up our product rule, f is going to be the first function, g is going to be the second function. So we would separate it like this, ax and e to the negative bx. Then we need to find each of their respective derivatives. The derivative of ax is just a, right? So if we had 5x, the derivative would be 5. If we had 10x, the derivative would be 10. If we have ax, the derivative is just a. For e to the negative bx, whenever we have a constant up in the power, that constant gets multiplied to the derivative of the function here. So with this negative b comes out from the power. I like to put my constants in front. You could certainly multiply it on the other side. That would be fine as well. So now that we have the pieces, we want to put them together to get the derivative of this function. So we're going to do f prime times g. So we have a times e to the negative bx plus g prime times f. But since there's a negative here, I'm going to write negative b e to the negative bx times ax. So again, it was plus, but since this was a minus, you could do plus negative. It's the same thing. So our first derivative looks like this, and we're interested in when that equals 0. So I'm going to do some rearranging of the second term before I think about factoring it. So the first term I'm going to leave alone, a e to the negative bx. But the second term, the a and the b are both constants, so I want them to be together. So I'm going to pull the a to the front. So I have minus ab, and then I'm also going to pull the x to the front. You don't have to do this if you don't want to. It's a matter of preference. I just like to write things in the order of constants, and then x terms, and then e's. Okay, so again, these are the same. I just rearranged the second term a little bit. Okay, so now I have something that looks like this. This is not like a simple algebra situation here. I have to do some factoring. And so again, I'm going to look at each term. And again, I'm going to identify what the terms are. So the first term is this one here. The second term is this one here. And I'm looking for what they have in common. And so again, I start with the constants, which aren't actual numbers here. They're just representatives. But I notice that they both have an A in them. So I'm going to factor out the A. And then e to the negative bx. Both terms have an e to the negative bx. So when I look at what's left, I notice that from the first term, I took everything. If I've taken everything, I'm left with a 1 as a placeholder, so that if I were to multiply it back in, I would just have everything I started with. And then from the second term, I've taken the A and the E term, so I'm left with a B times X. Okay, so now I have two factors equals 0. Okay, now you may or may not know this, but E functions will never, ever equal 0. They don't cross through the x-axis, which means that if you have a constant times e to the negative bx, right, that will also not equal 0. You can plug in, 1 and 2, 2 and 3, -4 and 7, and it won't cross through the x-axis. So since this term number 1 will never equal 0, I can just focus on term number 2. Okay, so if I set 1 minus bx equal to 0, I can bring the bx to the other side, divide both sides by b, because as a reminder, we're trying to solve for x. And I get x equals 1 over b. So my critical point here, the point that will make the derivative of this function equal to 0, is the point 1 over b. So again, if we're doing this in a more generalized fashion, we are being really careful with our constants like a's and b's and c's, and we're treating the derivatives using our rules and then the algebra while just holding in our mind that they represent some constant that we don't know what it is. Okay, so that's how we get the derivative and the critical point of the second function. And again, these are more generalized. We don't do this as often as we do with, actual numbers like we were doing before, but it does come up occasionally. So that's how we would treat it. Okay, so now that we've done those types of critical point problems, the question becomes, well, once we have our critical points, how do we know if they are local maxes or local mins, or neither? Because sometimes we have what are called tricky critical points, which end up being neither. And it turns out that the way we classify these depends on the type of information we have, and that there's 3 different tests that we're going to use to classify critical points. So we're just going to talk about the first test today, and on Thursday we'll do the other 2 tests. But we need to figure out how we classify. And when I say classify, I mean determine if our critical points are local maxes, local mins, or neither. And so to kick this off, we're going to think about this particular problem here. This is one we did at the beginning of class. So I will quickly remind you how we did this one. This should be in your notes at this point. So the derivative here was 12x squared. Oh, no, we didn't do this one. We didn't do this one. That's okay. So when we do the derivative here, we have 12x squared minus 12x minus 72. Okay, so again, first derivative, we want to know when does that equal 0, right? So this is the algebra part. So step 1, what we're doing right now is to find critical points, right? So that's what we've been doing all of class, is step 1 of this process. So when we look for the critical points of this function, we can use the quadratic equation or we can factor it. I prefer factoring. So I'm going to pull out a 12 here. And when I pull out a 12, I'm left with an x squared minus x minus 6 equals 0. Again, if you prefer the quadratic equation, that's fine. And then I'm going to factor it again by factoring this, what's left in the parentheses, by finding two numbers that multiply to give me -6, but add up to give me -1. And I get x minus 3, x plus 2. And then again, I'm going to take each factor and ask, when does that equal 0? 12 does not equal 0, so never. X minus 3 will equal 0 when x equals 3, and x plus 2 will equal 0 when x equals -2. Okay, so that's our first step. Now, the first test we have about classifying critical points is how do we classify them if we have information about the original function, so about f of x. And so when we say information about the original function, it's typically a graph. So if we have the graph of the function, how do we classify the critical points? Okay, well, let's look at the graph. Okay, so f of x looks like this. And we said our critical points happen at x equals 3 and x equals -2. Okay, these were our critical points. And this is going to seem really silly, this first sort of way we classify. But we're literally going to look at whether it looks like a local max or a local min. So if we go to 3, which is here, and we go down to the critical point, because we know it's where the tangent line is equal to 0, we can visually see that this is a local minimum, right? And if we go to -2, so we come over here, so -2 is right about here. We go up, we find the place where we have the horizontal tangent line. We can visually inspect this and see that it's a local max because it's the top of a hill. So how do we formally think about and talk about what we're doing when we visually inspect? Okay, so the rules look like this. So suppose that P is a critical point of f of x. So that means we've determined the critical points. If f of x changes from increasing to decreasing, so if we're going up and then down, then we have a local maximum. So we're visually looking to see, does it create this hill? If f of x changes from decreasing to increasing, then we have a local min. So that means we're going in the downward direction, and then we're going up. So it makes this U shape. Then we have a local min. And if it does not change at the point P, then it's neither. So we don't have a case that's happening in this particular problem where it's neither, but what you would see in sort of a neither case is something that looks like, you might have a local min and then something like this. So right here, we have a critical point because it flattens out for a minute, but it doesn't create a local max or a local min. It's kind of a weird flat spot. That's what you would look like visually to say neither, okay? That doesn't happen very often. So what does that mean for what we're doing? It means that if we are using the first derivative test, we are still finding our critical points as we have before, but then we are comparing it to the graph of the original function to determine what it's doing. So let's look at an example of this. So suppose that f of x equals 3x squared plus 6x plus 1. Use the graph of this function to classify the critical points as maxes, mins, or neither. So what you need to do here is you need to find the critical point by setting the first derivative equal to 0. And then you want to use your calculator to graph this function to see if at that critical point or critical points, if it looks like you have a local max, a local min, or neither. Okay, so I want you to try this. I'm going to give you 2-3 minutes. If you don't have a graphing calculator, I think you can probably work out what this graph might look like by plugging in different values of x and kind of plotting it, because this one's not too crazy. But try it out, find the critical points, draw a picture, and then determine if that critical point is a local max, a local min, or neither. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. Okay, so we need two things to solve this. We need the derivative function and we need a graph of the original function. It doesn't actually matter which one you do first or second, but I'm going to go ahead and find the critical points by using the derivative, right? So if we take the derivative of this function, we have 6x plus 6. We want to know when does that equal 0. So we bring the 6 over and divide by 6, and we get a solution of x equals -1. Okay, so now we need to graph the original function to figure out what's happening at -1. So if you were to graph this on a calculator or by hand or on a computer or whatever you're using, what you're going to find is you're going to have a function that looks roughly like this, where -1, right, is right about here. And so when you visually see what's happening and you go to -1, you see that our critical point here happens in an area that makes it a local minimum, because at the bottom of a cup, it's the lowest point in a small area. Okay, so having that picture is going to be really helpful in order to figure that out. Okay. Let's see. So let's do one more, mostly because I think we already did the derivative of this function. So here we have 2x cubed minus 3x squared minus 36x plus 14. This is the one that we did earlier, not the one I was talking about before. So we want to use the graph of this function to classify the critical points. So I want you to take 2 minutes. You can look back at what we found the critical points to be and how we factored that. But then you will need to graph the original function to determine if those critical points are local maxes, local mins, or neither. Okay, so I'm going to give you 2 minutes and I will again write out the derivative and the critical points, but it's going to be your job to graph it and classify them. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 seconds. Okay, and I did this on my calculator just so I can show you the input in case you have a similar calculator. So if you are trying to graph this on your calculator, you're going to be using the y equals function. So you just enter the function, 2x cubed minus 3x squared minus 36x over here plus 14. And then I hit graph. I had to adjust the window a little bit. Since I had found my critical points were at 3 and -2, I adjusted my x values to go from -10 to +10 because that would put the critical points between them. And then I had to make my y's pretty big to find them. But you can see that I see now what this graph looks like. So if I'm thinking about what's happening at -2, I come over here to the negative side of the axis. So -2 is right here. I can come up, I can see that this is a local max, right, to the left. So x equals -2, it's a local max. And then x equals +3. That's the positive side of the origin here, and the y-axis to the right. So I go 1, 2, 3. I can see that the horizontal tangent line is down here. So that's going to make 3 a local min. So it's a really good idea to be comfortable graphing things on your graphing calculator because it's always a good idea to check the original function to make sure it matches what you're saying that the critical points are. You can always double check that on a graph, and that's good practice. Okay, so we'll stop here. We'll pick up with this on Thursday. Try some of the early homework on critical points, and then we'll keep classifying on Thursday. Have a great rest of your day.